Good afternoon, everyone. So I come more from a computer networking background, and I'm going to give you a little bit of talk about, looking at the Internet of Vehicles and probably about applications of blockchain for securing vehicular networks. I guess this should be, yeah. Yeah. Okay, so this is sort of the outline. I'm going to give you a brief overview of vehicular network security issues, and then maybe talk about how blockchain may be applied in those scenarios. And I'll give you an example from one of the works that one of my students did quite a little bit ago about applying blockchain for trust establishment in the Internet of Vehicles, and then maybe end up with a brief discussion on open problems. All right, so, as technology has been progressing, we see vehicles increasingly being fitted with sensors of different kinds. They're collecting all kinds of data. And what we also, oops, I pressed the wrong way. And what we also see is that, previously vehicles were standalone. They would have sensors, they would collect stuff, but the data would stay on the vehicle itself. But now what we see is the vehicles have connectivity. They can transfer their data to the internet on the fly, right? While they're moving, they're connected to roadside units, and then they can transfer their data. And taking this even further, you can imagine that the data goes up somewhere in the cloud, and you analyze it, maybe get some insights into your movement patterns. You can monitor your traffic. You can control your transportation system, gain efficiency, and so on, right? So that's sort of, this is sort of an evolution of where intelligent transportation systems have evolved over the last 30 years or so. So starting with something like a simple intelligent system where you would have roadside sensors, and they would monitor vehicles going by and then maybe control the traffic lights a bit. We have gone to the cooperative intelligent systems where you get data from multiple sources, analyze them all at the same time, and then take decisions. And now we are sort of in the era of the Internet of Vehicles, where, maybe to some extent I do feel it's a buzzword where we say Internet of, X, Y, Z. But Internet of Vehicles refers to the fact that, you have a scenario like this. You have connected vehicles, you have autonomous vehicles, they're collecting data. You have roadside units, you have sensors by the road, they're all collecting data. And then you use your AI, machine learning, whatever is the flavor of the day, to get insights, and then these are sort of the benefits that we are looking at the end of the day. The main source of data in this case would be your vehicles. The vehicles currently are mainly in the form of, maybe I would call them smart vehicles. They have various sensors. And maybe going forward, we would get into the era of fully autonomous vehicles, level 4, level 5 autonomy. And these things generate a lot of data. And whenever we are generating a lot of data, there's valuable use for that data. The data may be misused. We sort of get into the problem of security for that data, or securing that data. And here's one example of a car. And if you look at a vehicle, there's also internal communication and external communication on the car. You've got to secure your CAN bus and other things which is inside the vehicle. Of course, that's one part of the security. And then the other part is when your data leaves the vehicle and goes out into the network, right? How do you secure that part? And just to give you some common examples of what attacks might be. So this one is a very simple, maybe, at most a mischievous one, right? What it happens is this guy wants to go fast, so it tells this guy, hey, there's a, in the intelligent transportation system, the vision is that vehicles will exchange messages with each other. If there is an accident going to happen, the car in front tells the car behind, hey, slow down, right? That kind of environment. So this guy is mischievous, tells this guy there's congestion up ahead, so it turns out, and then the road is free for you. A very, very simple kind of attack. Something more maybe, a malicious user might tell one vehicle to slow down and the one behind to speed up. And in this case, we have increased risk of collision. Another example, and this is about repudiation. In the case there's an accident, maybe there is a footprint of you in that neighborhood, in that vicinity, but later on you claim that I never generated that data, and then you say I was not at the accident site. Another important concern, of course, in vehicular networks You are constantly transmitting messages to vehicles around you, telling them about your movement patterns, maybe whether you're speeding up, whether there's an accident, and so on. So it's potentially possible that I can track you, right? By looking at your identity, the footprint you're leaving, it's possible to track your movement patterns. Maybe I can figure out where you live, where you usually go, and things like that. So there's a privacy risk. Now, when it comes to challenges of security in this Internet of Vehicle kind of scenario, there are some things that set it apart from your traditional computing systems. So, for example, one is there's a trade-off between the need for doing authentication with a single identity versus privacy. Of course, organizations such as, if you always maintain a single identity, you can protect against cyber attacks with multiple, where you take on multiple personalities and then inject messages. Or a police force would probably like for you to have a single identity, then we can track exactly what you have done, right? However, users may value their privacy and they may not be very happy with that. Right, so there's a trade-off between me trying to maintain my privacy through maybe, for example, the use of pseudonyms, and then there are other organizations who would want me to maintain a single identity so that it's easier for them to do their job. Another issue here is that you can consider a vehicle to be more of a real-time system. It needs to take decisions in the split second. In those cases, if your validation, verification, authentication, these things take a lot of time, then it's of no use. And then the other problem is we have mobility now. Vehicles inherently are mobile. Since they're mobile, the time you can visualize or you interact with the vehicle is pretty small. So then think of something like a reputation-based system to establish your trust in an entity. Most reputation-based systems would be based on an interaction and then assigning a score of trust to that particular entity over time. But if you don't interact with somebody for very long, then of course you cannot use reputation-based systems. This is just an example. Key distribution. There are multiple parties involved here, right? You have to trust all vehicle manufacturers. Maybe I trust manufacturer A of country X, but I don't want to trust manufacturer B from country Y, right? But then in an ecosystem like this in Singapore, you may have vehicles from multiple countries coming in. So how do you do key distributions and so on, right? And then again, Singapore may be a little bit easier in the sense that this is a small single country, but even if you think of United States, and each state has its own department of motor vehicles, getting them to agree on things and cooperate can be challenging. Okay? So that's sort of a very quick overview of some of the security issues in vehicular environments. And maybe now I'll talk a little bit about sort of a survey on what people have done in terms of the applications of blockchain for security purposes in vehicular networks. Of course, some key requirements of security in Internet of Vehicle or vehicular networks. We want integrity, we want to be able to authenticate and so on. These are fairly standard requirements for security in any system. And then blockchains bring in many advantages of their decentralization, transparency, the use of pseudonyms, and that helps in maintaining privacy and so on. And then also availability, which is a function of the decentralization of the blockchain. If you look at a typical architecture that depicts how a blockchain may be used in a vehicular network, this would be probably the go-to picture. And the way you see it is you have vehicles. Vehicles would usually communicate with roadside units. And these roadside units, in order to authenticate the vehicle, would talk to a trusted agent of some kind. It could be the government, could be the Department of Motor Vehicles, whatever. And then usually you would interact with the blockchain either through these roadside units, or sometimes you may talk directly also. Okay? This is a typical architecture like this, and then based on this, you come up with many different solutions. So for example, blockchain applications have come up in terms of privacy, security, trust, and so on. And there's a whole wide range of literature that's been done over the last 5-10 years. Just to take one specific example, if I look at trust management in Internet of Vehicles, here again you see a lot of work and people working on these things. And I'll talk about this particular one here in just a little bit. In terms of what I want, this just to give you a bit more of a flavor of the blockchain work in this environment. In terms of what we want, this is my desiderator, right? My list of desirable properties I would want. Of course, in a vehicular environment, I would want high throughput, low latency, maybe energy efficiency, maybe not critical, but still I would want that. And I want various kinds of security and maybe not a single point of failure, not a single administrative domain that I trust. And we have different kinds of blockchains that offer different groups of these properties to us. So either we can go for permissioned or permissionless. Each one has its own advantages and disadvantages. And if you look at what people seem to prefer in the community, so, most of the work seems to go towards permission just because of latency issues and making sure that we can have more transactions and so on. That's the primary motivation. Most of the work is based on permission blockchains. And then again, if you look at specific examples of what people tend to assume in their literature, hyperledgers are probably a little bit more popular than Ethereum. Yeah. All right, so now that was sort of a very, let me see, it's 3 o'clock. Yeah, so I think that was a very quick introduction to the existing literature on the use of blockchain for vehicular security. Right? So let me now spend a little bit of time on one specific example of the use of blockchains. And this is in the specific context of trust establishment. And this is the whole problem here. So, there are many vehicles on the road. So it's inherently a non-trusted environment. And the problem is that the mobility of the vehicles, the fact that you don't spend too much time in one area or you don't interact too often for very long with any one particular vehicle, makes it difficult to establish trust and use reputation-based systems. And of course, we would like in such a system that any data transfer should only happen after I have established the identity, or at least have established the trustworthiness of the vehicle that's generating the data. That's one. And then the other thing, and this is sort of the motivation for the work that we did, was more in terms of one particular concern here is the physical security. If you look back, if you remember our picture there, right? So the main players in this kind of environment are your vehicles and these roadside units that you interact with. Roadside units are deployed by the roadside. Now, Singapore happens to be a very safe country, right? Nothing bad usually happens. People are law-abiding. But imagine, can you really trust pieces of equipment that are deployed by the roadside and nobody will touch them, nobody will play with them? Even when you take your car to a mechanic or to a garage, your car, let's say, has its own identity, has its own secret keys that are stored in the memory. Now, you have given your car to the garage for maintenance. Are you sure that the mechanic is not looking inside your car and trying to figure out what the keys are? So that's the part about physical security, where the adversary may have physical access to your equipment. And if I have physical access to your equipment, I could do a few things. For example, if there are any open ports, I can connect to that port and then try to read the contents of your memory. And if you have stored any keys somewhere, I can figure out those keys. Even if there are no open ports, I can do side channel attacks. So for example, if your processor is running, let's say the roadside unit, the processor is running, I can take an antenna nearby, pick up the electromagnetic waves that are coming out of the processor because it's consuming electricity, transistors are switching on and off. By looking at the EM wave, the electromagnetic wave radiations from those processors, I can figure out what your key is, right? So those are all well-established attacks. So now we have to worry about making sure our system is secure against these physical attacks. So this is sort of our architecture here. So we have various vehicles on the roads, and again, they talk to these roadside units. And then this is where our blockchain is, and there's a smart contract there that acts as the enforcer. So the smart contract makes sure that only authorized and trusted vehicles are allowed to access the blockchain and transfer the data there. There are 4 things that we try to achieve here: scalability, decentralization, low latency, and security. So scalability comes from 2 parts for us. One is we try to minimize the communication overhead that we need. And then we use a dynamic proof of work where the hardness of the problem varies depending on the level of congestion in the network or the number of users in the network. The decentralization part is quite straightforward. And the low latency comes through the use of something called these physical unclonable functions that I'll go into just now. And of course, the security comes from 2, the immutability of the ledger and also the use of those physical unclonable functions. In terms of what we think about the adversary, the standard you live now model where the user can read, write, intercept any messages in the network. On top of that, we also assume that the adversary can get physical access to your vehicle and then try to tamper with it. So now let's come to this physical unclonable function part of things, right, which is supposed to give me protection against these physical attacks. So these are basically the same as our fingerprint that we have on our fingers. I hope that's okay. Yeah. Too bright. Yeah. So what we would like is, I want to get out of relying completely on keys that are stored in my memory. Right? So one way of doing that is by assigning hardware-level fingerprints to each device. And these fingerprints are dependent on the semiconductor chip, maybe your processor, maybe your memory, whatever, some piece of semiconductor that you have in your device. If you are familiar with the IC manufacturing process, so for example, what we would do is we would have a layout like this of a wire that goes like this, and we try to do this in the clean room through a sequence of steps such as etching and stripping, and you have a mask, you shine some ultraviolet light through it, then you go through a sequence of stripping, etching, and those kinds of steps. What happens is, after you manufacture, you never get these nice-looking straight 90-degree angles. Also, if you have designed this wire to be, let's say, 10 nanometer, you're never going to get 10 nanometer. Sometimes you will get 9.5, sometimes you'll get 9, and so on. And this is just to show that. For example, if this is still older generation technology, if you're trying to make wires or gates of certain length, there will always be some variation around it. You'll never be exact. And this is just because of the randomness that occurs during the semiconductor manufacturing process. No matter how hard you try, there will always be some random variation. So I make the same circuit today, 9 a.m. in the morning, and I try to repeat the same process maybe half an hour later. There'll be some variations. These minor variations may not matter when you're just creating a memory or a CPU, but I can exploit this to create functions that are unique to your particular chip. And one way of representing that is through these physical unclonable functions, and I represent them as a function here. So if I give a certain bit sequence to your chip, you will give me a unique response. And if I give the same bit sequence as input to some other chip, exact same design, it will give me a different response. So it's just like a fingerprint for your semiconductor device. So this is something we integrate along with everything else, along with the blockchain for our security. So while the blockchain comes in and gives us, so we are using a dynamic proof of work thing here. And then the perfs are the ones that come in and give us the hardware root of trust, and that cannot be tampered with. And usually if you try to guess, if you try to tamper with this, you open it up and to see what that function is, you usually destroy the chip. So you cannot play with that. So this is sort of a very quick overview of the protocol. So there are 2 phases. There's one, the setup phase, and then there's the data transfer phase. In the setup phase, when the vehicles come in, They interact with the enforcer contract. And there are databases that store these challenge response pairs, these guys. This is my challenge response pair. So there are databases that store these challenge response pairs for every vehicle. There's a registry, and then there's a certificate registry for every vehicle. So when a new vehicle comes in, you have to register, and then you also have to upload at least one of your challenge response pairs with that. And this is just the data structure of that. And subsequently, when you want to transfer data, you go to the RSU and say, I am such and such, I would like to transfer data. The RSU sees whether you have a certificate or not. And if you have a certificate, you're authorized. Otherwise, what it does is it sees if you're registered or not. If you're registered, then it issues you a challenge, which you have to solve by using your physical and clonable function. That's the very high-level overview. Right? And this is sort of the protocol here. So when you want to establish your identity, you tell the RSU who you are. The RSU issues you a challenge, and you can only sort of sign that challenge using a response that you generate from your physical and clonable function. And only the person who owns that specific semiconductor chip can correctly solve that puzzle. These are some results in terms of security. No need for any proofs. So just to show you how this thing costs, so in the smart contract itself, there are various functions that we had for registration, for issuing certificates and so on. This is the cost and way for each one of those functions. And, I was talking about a dynamic proof of work, and depending upon what kind of vehicle arrival rate you have in your system, you can dynamically adapt the proof of work difficulty level so that, at least when the arrival rates are very high, you can opt for a smaller or a less complicated proof requirement. There are a couple of slides that show how our communication overhead, that increases linearly and much slower than what was at the time the state of the art in the system, in the literature. And same thing in terms of authentication delay. We of course, we increase linearly with the number of vehicles, and the rate of increase is lower. We also did some simulations of these vehicles in real life. So there's the simulator called Sumo, and you can use it to create realistic traffic traces for any city. So for example, I think this is Chinatown in Singapore, so you can take this section, and there's a zoomed-in portion of somewhere in this Chinatown, and you can design how many lanes are there, what buses, cars, and so on, and then you can generate realistic traffic traces. And once you have that, we would simulate this in the network simulator NS3. These are some, if you're into wireless networks, you would probably find these very relevant. So these are the network parameters. And then these are results that show how much improvement we have over the state of the art previously for various things. All right, so now maybe sort of trying to close down in terms of what I feel are still open problems in this area. Of course, there are standard issues which we talk about when it comes to blockchains and smart contracts and so on, right? Of course, blockchains have forking problems, the majority attacks, usual standard stuff, right? And there's still, I feel, at least in the context of vehicular networks, where latency is critical, we need to make decisions in the order of few tens, maybe hundreds of milliseconds at best. Probably these things are still a bit of a challenge at this point. Okay? And there are similar issues with smart contracts too. For example, reentrancy, loops can trigger you exhausting your gas limit and so on. Then there are a couple of other things that I have is, if you look at most of the work that's done in terms of blockchain and vehicles and so on, none of them exist in real life. They're all simulation-based studies and maybe some small-scale things. So real-life integration is still, I think, a problem, and I don't think that there exists a proper solution that's acceptable. Going forward, I think everybody likes to talk about quantum safe stuff. Of course, we don't know anything about the hash function being unsafe to quantum attacks as yet, but we don't know what happens. So that's something, of course, we need to worry about. There are no security standards as such for the contracts that we were talking about. And of course, in a car, the energy concern may not be as much as compared to maybe an IoT device or even my phone, because they can when the vehicle moves, it can charge up. But still, I believe energy efficiency is a concern. And then finally, of course, I can publish papers saying blockchain and vehicles, but then the real question is does it make sense, right? And here's a flow chart which you may or may not have seen before that talks about whether we need a blockchain for something or a traditional database is good enough. So this is sort of my last slide, and just to conclude that security happens to be an important problem, and I do think blockchains have some use in solving some of these problems in the vehicular network context, but there are still certain hurdles that we still need to overcome. So thank you very much, and thanks for inviting me here today.
Thank Professor Sikdar for the valuable insights. We still have some time for Q&A. Who would like to be the first one to answer any questions? Okay, the orange shirt.
Hi, Professor. My name is Kenneth, and I'm from SOC. My question that I have would be that understanding that you have a linear way of your communication, as well as the decrease of difficulty level for the network congestions and the arrival rate. So my question will be, will you consider a multi-party computation method so that possibly it could go down logarithmically? And because many vehicles in the same area might be producing the same information. So it does, I guess to me, it does make sense to actually logarithmically generate a multi-party computation and submit one signature into the chain.
Right. I agree that in many events of interest, there may be multiple vehicles in the vicinity, and they can do some kind of multi-party thing and then upload once. That part, the data upload part may be fine, but then again, even if you want to do multi-party computation, for example, you want to be able to trust those people to do, let's say, you only want to involve those parties that you trust. So the first step would still be to establish whether these 4 vehicles around you or 5 vehicles around you, are they trustworthy or not? So at that part, again, that part you cannot escape. You still have to interact with some, let's say in this case, that was my enforcer contract, which validated whether you're a real user, you're a trustworthy user or not. Once that step is done, then you can go into all these other things, such as multi-party computation, to reduce the overall number of transactions that are finally sent into the blockchain. Yes, that's possible.
Thank you. Thanks.
Any other questions? No? Okay. Hold on. Anyone could give you some microphone?
Hi, Professor.
Hi.
I'm just a student of NTU, and I think you just bring us a very interesting topic, the application of blockchain in the transportation area. And for now, my question is, a lot of countries like China, United States, they all have like many cameras on the street, and these monitor the traffic. And so I would like to know, is the blockchain technology just inserted into those machine, and so that everything they can be tracked? And then I think it's a very good application for this is just like to decide who to blame for a car accident. Yeah, and yeah, I would like to.
That is definitely one possible application of blockchain. But to the best of my knowledge, right now, they don't use a blockchain for that. All the data that is collected usually goes to either a regional data center or a central data center. So it's not stored on a blockchain, it's stored on a database somewhere, one single traditional database where all the video feeds are coming in. But yes, if you want a transparency, for example, that I would like to view my own video and make sure everything is correct. If somebody has sensed that I was in a certain position at a certain time and you're blaming me for that accident, I want to be able to verify it. In those cases, maybe having transparency that comes through the use of a blockchain might be helpful.
Thank you for the question. Now let's welcome Professor Wen to give the appreciation word to Professor Sikdar for his excellent speech and Q&A. Also give some applause to them.